All right, welcome to chapter 10.3, which is where we're going to start talking about least squares regression. In the last two sections, we've used the brain weight versus head size data, so we'll keep using that through the rest of this chapter because it's a nice, convenient, and relatively interesting data set. All right, so it's very convenient for us to be able to visually see the relationship between head size and brain weight. And it's pretty easy to assess the amount of linear association using that correlation coefficient that we talked about in section 10.1 and 10.2. But if I measure somebody's head and find out that it's 4,700 centimeters cubed, how do I estimate the brain weight that corresponds to that head? So generally you can't decapitate somebody to collect data without facing murder charges. But I don't have a data point at 4,700 centimeters, so how do I know what the value should be for that point? So the goal of fitting a linear regression is to solve that dilemma and make it so that you don't have to necessarily go out and collect new data for every possible value of the explanatory variable, as long as you have enough values to kind of get a sense of what the relationship should be. If we fit a linear trend line to the data that we have, that line would give me the best estimate for what the linear relationship is between x and y, and it lets me predict the average value of y for a given x value. Now you'll notice that word average value of y, we're not predicting what an individual observation will be that happens to have that x value. We're predicting what the average of all observations that have a specific x value will be. Okay? The equation of a line, this is even outside of statistics, has the form y equals ax plus b. When we start talking about data, though, we want to indicate that we are predicting a value, right? So we add a little hat on top of the y and say y hat equals ax plus b, where x is the explanatory variable, y hat is the prediction for the response variable, a is the y-intercept, which is the predicted value when x equals 0, and that may or may not make sense in the context of the problem. And b is the slope. And what the slope means is if I change the value of x by 1, what does my prediction for the average value of y change by? All right, so that's how you interpret the slope. In the graph on the last slide, the equation of the regression line was y hat equals 325.573 plus 0.263 times x. So those parameters, that a and b value that we've estimated, and we'll talk about how to get those values in a minute, but those numbers have meaning, right? So if I had a head size of 0 cubic centimeters, then we'd expect a brain weight of about 325 grams on average, right? Now, physically, this makes no sense. If we have a head size of 0 cubic centimeters, we don't have a brain either, right? There's no volume. But because of the data that we have no points at x equals 0 either. So it makes sense that the relationship isn't necessarily interpretable across every possible value of x. We're going to confine ourselves, generally speaking, to predicting for values of x that make sense. 0 is not one of those values. So you can't always interpret the intercept in a way that makes sense in practice. Sometimes you can, sometimes it's actually a useful value to know, but it doesn't always make sense. Okay? The slope, however, generally speaking, has a physical meaning, and that is if we have an increase in head size of 1 cubic centimeter, then our predicted brain weight will increase by 0.263 grams. So the sign of the slope is going to always be the same as the sign of the correlation coefficient. If the slope is negative, that indicates that we have a negative relationship between x and y, which also means that we have a negative correlation coefficient. Both the correlation coefficient and the slope provide some information about the direction of the association. One thing that we have to be careful of when we are working with linear regression and predicting based on linear trends is we have to avoid extrapolation. If we predict values for the response variable using things that are outside of the range of the explanatory variable that we have, that's called extrapolation, and it can lead to very misleading predictions. So in this particular XKCD comic, they got married, and so there's a nice 2-point linear plot, right? We have yesterday, 0 husbands, today, 1 husband. If you predict out over the course of 60 days, you have a ton of husbands, okay? So, obviously, this is ridiculous, but it's a good example of something that people have a tendency to do even in less ridiculous circumstances. And even in those circumstances, you can still end up with very misleading predictions. All right? So, just something to be cautious of. Now, if we wanted to predict values for the response variable for an explanatory variable value outside of the range of our data, for our brain and head size data, one way to do that, we have data from adults. What if we wanted to predict the brain weight of a baby? And this data was included in the original publication, but it wasn't included in the data set that I've been using. We have an X value of 1,212 cubic centimeters, and we want to predict Y hat. Now, if you remember back to that graph, none of our X values were this small, right? So go ahead and plug that 1,212 into the original regression equation, and we get a predicted average brain weight of 644.85 grams. Now, because I pulled data from the original paper, we actually have the value of the weight of the infant's brain, and it was 490 grams, which means that we can calculate out how wrong were we. Our prediction had an error of negative 154.850 grams, all right? And that error is called a residual. Now, this residual is actually not that bad. Maybe the extrapolation wasn't so extreme in this particular case, but the lowest observation we had was 2,720 cubic centimeters, and that's more than twice what we actually just tried to predict. So we're really outside the bounds of a reasonable prediction based on what data we have. All right. Now, there are times when extrapolation is reasonable. There are times when it's not. So I want you to think through the following scenarios and decide whether you think it's reasonable or not to extrapolate and predict these values. All right? And I encourage you to think about the reality and the real constraints of the data, as well as the statistical meanings and how far away the points are from the range of the data. Okay, there are physical constraints that statisticians have to deal with that make extrapolation defensible or not, and it's worth thinking about those. So pause the video for a minute and decide whether you think each of these is reasonable. All right, so if I have data on the foot length and height of 58 people, ranging from 4'10" to 6'1", and I want to predict the foot length of someone who is 4'2", that might not be the best idea. Most adults are taller than 4.2, or 4 feet 2 inches, sorry. The relationship that we have for adults may not hold for children, who would normally potentially be at heights like that. And even if we had an adult that was at that height, they might have some sort of medical condition that would also affect foot length, so our data might not generalize well to that particular prediction anyway. So I would say that 4 feet 2 inches is probably not something that we really want to predict. If we want to predict something for someone who's 6'3" though, that's probably okay. We're only 2 inches away from the data that we have, so we're extrapolating by a tiny amount. 6'3" is not an unusual height. So there's no reason to think that the linear association that we have wouldn't hold for somebody who's slightly taller. So 6'3" is probably okay. We can extrapolate by that much fairly comfortably. But if we have somebody that's 7 feet tall, that's probably, again, not a great idea. There's not that many people that are that tall. The data from the general population might not represent those people well because, they might have some sort of medical condition that caused them to grow that tall. But that medical condition might also affect the relationship between foot size and height. So we just maybe aren't super comfortable predicting that far out. Okay. In the next scenario, we have data on how many ice cream cones were sold at a shop each day and the temperature for that day. And we've got observations for January through April. And I'd like to predict how many cones will be sold at a shop per day during July. Okay, so I think that that's maybe not the best idea. January to April has a pretty set temperature range. The temperature in July is going to be a lot higher and probably fairly well outside of the range of data that we have. The conditions are also different in the summer, so we might expect to sell more ice cream cones in the summer anyway. So the data that we have might not even hold. But if I want to predict how many cones will be sold during early May, that's probably okay. Early May has about the same average temperature as late April. If this is a ice cream shop in Lincoln, right now, even mid-April, we're still getting 80-degree days and we're still getting freaking snow showers. So, not that I'm bitter. All right. If we had an ice cream shop in a separate town, different town, that was similarly sized and the ice cream shop was relatively comparable to ours, maybe we could extrapolate and predict for that ice cream shop. But I'd be very cautious. I'd want to collect a little bit of data first to make sure that the two ice cream shops are similar in the respects that they have similar traffic and that sort of thing. If I want to predict how many cones will be sold at an ice cream shop in Saudi Arabia during May, that's a really not good idea. So the average temperature is much higher. The location is very different. There are different cultural issues. There's too many factors that are different for that to be a reasonable prediction, even if we still have the same temperature and temperature data that would let us predict the number of ice cream cones sold at a shop, right? So we have to consider a whole bunch of different factors when we're deciding whether something is extrapolating unreasonably or not. Okay, so thus far I've been avoiding the question of how do we get our regression line. And that's mostly because it involves, equations and math, and those tend to be intimidating. But let's talk conceptually, at least, about how we get the A and B values that correspond to our intercept and slope. And it's going to involve these residuals that we've been talking about. Okay, so the least squares regression line is the line that minimizes the sum of the squared residuals from the line. So y minus y hat squared. And there's an applet here that lets you play with that. And so here it's showing you that dials allow you to adjust the values, points let you drag things around. So here you can see how the line changes when you move different points around, and that's kind of cool. But down here, you can change the values of the intercept and the slope, right? And see how the squares change, and your goal is to minimize the total area of all of these squares in this particular display. All right, so you want a line that gets fairly close to all of the points, right? And you're just trying to optimize how close. Okay. So I encourage you to play around with this app and try to manually get a line like that minimizes the sums of squares. There's a similar app in the book as well that you can find the link to. I will say with this particular applet, there are multiple variables included here. I don't really think you need to worry about the multiple variable regression. We're not going to talk about it in this class. So only scroll down if you're interested, and it's not going to show up on the test or anything. Okay? Now, you may be wondering, why are we squaring things? And there's a couple reasons. One, it's equally bad if we have a negative residual or a positive residual, so we don't want to just add up the residuals because we're going to get 0 every time, as it turns out. So we have to figure out some way to make all of the errors positive so that we can minimize that. And it turns out that the absolute value actually gets mathematically hard to minimize. If you think about the sharp turns that absolute value functions have, it may start to make a little bit of sense why that would be. Statistically, it's generally just easier to square things. It has nice, smooth optimization functions, and makes for nice math when you're deriving this whole thing, which, thank God, we're not going to do in this class. But as a result, we're squaring things, which means that big residuals have a really, really big effect on the overall result. All right, so that's the biggest takeaway here, is that when we square the errors, the squared residuals, we are very much overemphasizing points that are far away from the line. Okay? Now, in terms of calculation details, if we want to get the slope, we take the correlation coefficient, R, and multiply that by the variability in Y divided by the variability in X. So this is just the standard deviation in Y and the standard deviation in x. All right? And once we have our slope, we can get our intercept by taking the mean of y and subtracting off the mean of x times the slope. All right, that gets us our intercept. Okay, so the calculation details are not actually that gory as long as you already have the correlation coefficient. And we've already said we're not going to make you calculate the correlation coefficient from scratch. So you guys are getting off pretty easy here, which means that if you see this kind of data on a plot, so the mean of x, the standard deviation of x, the mean of y, the standard deviation of y, and the correlation coefficient down here, you should be able to reproduce the regression line equation with just the 5 values that correspond to the mean and standard deviation of each variable plus the correlation between them. All right, so I've done the math here, and we do in fact get our regression line values. So far, so good. Math works. Yay! All right. Now that we have a regression line, though, oftentimes we want to measure how well does our data fit our regression line? How well does the regression line predict our data? And we do that with something called the coefficient of determination. Okay, so two different coefficients we're talking about here, the correlation coefficient and the coefficient of determination. We refer to the coefficient of determination as r squared, and as it so happens, it's literally the correlation value squared. So, because of that, it's always going to be between 0 and 1, where 1 equals perfect predictions, 0 is no relationship whatsoever. All right. The r squared for this particular plot is 0.639. All right, so what that means is that we are predicting 63% of the total variability in y with our regression line. Okay, so let's just look at what different values of r squared correspond to. All right, so from almost 0 to 0.13 to 0.277 to 0.446 and so on. And you can see that as r squared gets bigger, our points get more tightly clustered around our line. And notice that the slope doesn't really matter so much. What matters is how tightly clustered those points are around the line. Okay, so we can have a slope that's fairly shallow, corresponding to a b value that's relatively small, but if the points are tightly clustered around that line, then it doesn't matter that the slope value is small. Okay. Now, there's another interpretation for r squared here, which is kind of illustrated in this animation. So let's wait for, okay, so we start with the total variability in y, so how far each of the points are away from the mean. We predict a linear regression and look at the variability that our linear regression explains, right? So wait for 2 to come around again here. Okay, so that's the regression sums of squares, the regression variation. And then we look at the leftovers, so the sums of squared errors from our regression line. And what r squared is the percentage of variability, total variability, that we've explained by fitting the regression line. So it's the dotted line shown in 2 divided by the dotted line shown in 1. Okay? All right. So in math, we can write this as the total sums of squares, the sums of squared errors, which is what SSE stands for. So total error is equal to the sums of squared errors from the regression line, right? So the things the regression line doesn't explain, plus the sums of squared errors between the regression line and the mean. And so that's the stuff that the regression does explain. All right, so I'm using just slightly different notation than what the book is using because I think it's a little bit clearer why this would be true. You can see that y minus y hat minus y bar, the y hats would cancel, and you'd end up with the same sums of squared errors. All right. Which means in math, we can write r squared as 100 times 1 minus the residual errors over the total errors. All right. And this works out to equal the proportion of error in y explained by the regression. So that's where this whole interpretation of r squared comes from. If you remember, so if we return to our head size and brain weight example, we can see that r is 0.7996. We can compute r using the sums of squared errors formula because I've given you the 3 sums of squared errors in this plot. Then we can check and make sure that it's the same as this 0.7996 squared, just to make sure that the math checks out. All right. So we have r squared is the sums of squared errors of the regression, so SS reg, divided by the sums of squared errors of all of the variability in y. So that's the sums of squared errors, right? Okay. So back here, sums of squared errors, that's the total variability. Sums of squares regression is the stuff that our regression line explains. Sums of squared error is the leftovers that our regression line doesn't explain. And if we add these two up, they total up to the total sums of squared errors. All right, so that's where these numbers are coming from. Our r squared is 0.639, and it so happens that if you square 0.7996, you get 0.639. Great. Math still works. Everything is peachy. All right. So I'm going to recommend that you work through Exploration 10.3 in groups on your own, however you want. Ignore the parts that say compare with your classmates, because obviously that is a little bit more difficult right now. And if you do work through this, you can upload your answers to Canvas for extra credit. But you certainly don't have to do that. I just think it would benefit you to have another walk through an entire problem to kind of think through in a guided way all of the stuff that we've talked about during this chapter, because we have actually covered quite a bit of material in relatively few slides, I think. Okay? Alrighty. So you guys work on that. I hope that you are still healthy and safe and not going crazy. I am getting a little bit of cabin fever myself. So, alrighty. 2 more sections and we are done with lectures. That's, as I hope, as exciting for you as it is for me.